Hello students, welcome to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So today we are going to finish this chapter, that is chemical bonding and molecular structure. Okay, so now today is part 3 and we are going to discuss MOT, bonding in homonuclear diatomic molecules, and the very small but important topic, that is hydrogen bonding. Okay, so now you can join our WhatsApp channel, link is there in the description section. This will help you to get access to all our notes, PDF, everything. Okay, so you have seen the how are we going to complete this chapter. Okay, so it is like part 3 we are going to do today, MOT, bonding in homonuclear diatomic molecules and hydrogen bonding. Okay, now year wise weightage is just carries 1 to 2 years, every year you get 1 or 2 questions, but yes, among PU1 this is very important topic. Now coming to part 3, what we are going to study in MOT. So these are all the topics of MOT. So in MOT we are going to study about the features, then we are going to study about the LCAO, linear combination of atomic orbitals, then we are going to study about the conditions in which the atomic orbitals can combine, then we are going to study about types, then we are going to study energy level diagrams, and we are going to study electronic configuration and molecular behavior. Okay, so now if you see under this features of MOT, the first thing, that is the electrons in a molecule are present in the various molecular orbitals. Okay, the electrons in a molecule are present in various molecular orbitals, like how in atoms the electrons are present in atomic orbital, similarly in molecules the electrons are present in molecular orbital. Next we have the atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. Okay, so whenever we have molecular orbitals, it is due to the combination of atomic orbitals, and these atomic orbitals should have similar energy and shape. Next we have that when these atomic orbitals combine, we get two types of molecular orbital. One is bonding molecular orbital, another is anti-bonding molecular orbital. Now here bonding molecular orbital should be of lower energy and anti-bonding molecular orbital should be of higher energy. Okay, next we have molecular orbitals are filled in accordance with the Aufbau principle. Okay, so how, like whatever the rules are followed while filling the atomic orbitals, the same rules are followed to fill the molecular orbitals as well. Okay, this is the features. Now coming to LCAO, or linear combination of atomic orbitals. So you can see that suppose the atomic orbitals are represented by wave functions, that is psi. Okay, HA and HB, if there are two atoms, psi A is the atomic orbital of A and psi B is the atomic orbital of B. Now what happens here? We have sigma, which represents like when they have overlapping constructive interference. Okay, so two atomic orbitals or two wave functions have constructive interference, we get psi A plus psi B. Okay, and when we have two atomic orbitals of destructive interference, we call it as psi A minus psi B. Okay, so here we get bonding molecular orbital and we get anti-bonding molecular orbital. Okay, bonding molecular orbital is less energy, anti-bonding molecular orbital will have higher energy. So two atomic orbitals will combine to give you two molecular orbitals, one is bonding, one is anti-bonding. The next thing is the conditions. So they should have nearly same energy and they should have similar energy, they should have same symmetry. Okay, and next one is the overlapping should be very good so that the bond can be stronger. Okay, next coming to types. So under types we have sigma bond and pi bond. Now sigma bond is formed, like sigma bond is due to symmetrical around the bond axis. Okay, and pi bond is asymmetrical around the bond axis. Now we will understand this in detail. Now see, suppose I have 1s orbital and 1s orbital. Okay, so here what is happening, 1s orbital and 1s orbital is combining to give you sigma 1s. Okay, 1s orbital and 1s orbital combines to give you sigma 1s. So when this is minus means showing destructive interference, and we get anti-bonding molecular orbital here, sigma star 1s. Okay, now 1s and 1s will combine constructively to give you sigma 1s. Okay, and this is bonding molecular orbital. Got it? So now what happens, now see, if you see along the bonding axis, this is the bonding axis, and here also we have, this is the bonding axis, right? So in along the bonding axis, here also positive charge, here also positive charge. It is symmetry around the bonding axis. So that is why this is a sigma bond. Now if you compare 2pz and 2pz, okay, now 2pz you will combine like this, you have like this and you have like this, this is plus, this is plus, this is minus, this is minus, these two will combine to give you this one, minus plus minus, right. So now what happens, if you see this is the bonding axis, along the bonding side here we have minus plus minus, here also minus plus minus, means it is symmetry around the bonding axis, right. So this one will give you sigma bond, that is why. Now if you compare pi bond, that is the interference or 2px and 2px if it is combining, okay, we get positive charge, we get negative charge, and if you check along the bonding axis we have plus and minus, right. Along the bonding axis we have alternative signs, right. So that is why it will be giving you means due to this presence of this one we will have asymmetrical along the bonding axis. So that is why it is called pi bond, okay. So that is the meaning of sigma bond and pi bond. In sigma bond along the bonding axis symmetry is there, in pi bond along the bonding axis there is no symmetry, okay. Now coming to energy level diagram, so here it should be very careful. See now how in atomic orbitals we have the energy levels, right, 1s, 2s, then 2p, 3s, 3p. Similarly in molecular orbitals also we have the energy level order, okay. Now how we can see, now if you see for lithium, beryllium, boron, carbon, nitrogen, we follow the order first sigma 1s, then sigma star 1s, then sigma 2s and sigma star 2s. After sigma star 2s we have pi 2px, pi 2py, and then we have sigma 2pz. Then we have pi star 2px, pi star 2py, and then we have sigma star 2pz, okay. 1s, 2s, sigma and sigma star, 2s, 2s, sigma, sigma star. Then for these elements we have pi 2px, pi 2py and sigma 2pz. Then we have pi star 2px, pi star 2py and sigma star 2pz. Now coming to O2 and F2, there is a slight change here. In O2 and F2 what happens, the sigma 2pz will come here and the 2px and pi 2py will come here, okay. So there is an order change here, okay. You can see here 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px, pi 2py, right. First sigma 2pz, then it will be pi 2px and pi 2py, okay. Next we have pi star 2px and pi star 2py, then we have sigma star 2pz, okay. Clear. Then we have now coming to the electronic configuration and molecular behavior, okay. So now in electronic configuration we have two important things, that is bond order and magnetic behavior. How can we predict bond order, okay. In bond parameters we have discussed what is bond order. So with molecular orbital diagram you can see bond order is equal to half of NB minus NB. So what is NB here? NB is number of electrons in bonding orbital, okay, in bonding molecular orbitals, and Na is the number of electrons in anti-bonding molecular orbitals, okay. Half of that will give you bond order, okay. Next coming to magnetic behavior, so here also we have two parameters. If you have diamagnetic means no unpaired electrons, okay, no unpaired electron, and then if it is paramagnetic we have unpaired electrons are present here, okay. Now when we do questions it will be much more clear. Now coming to bonding in homonuclear diatomic molecules. Now see, H2 means there are two atoms in H2, total electrons is 2, first orbital is sigma 1s, so sigma 1s2. Now if I want to calculate here half into number of electrons in bonding minus number of electrons in anti-bonding, that is 0, it will give you 1, right. Now there is no unpaired electron, so it is diamagnetic, okay. Now if we come to helium 2, helium is hydrogen helium, right. So helium is having 2 electrons, so 2 helium will have 4 electrons. So sigma 1s2, sigma star 1s2. Now if I want to calculate bond order here, 2 minus 2, that is equal to 0. Now when bond order comes out to be 0, that means the molecule does not exist, okay, does not exist. Now if you see lithium 2 is having 6 electrons, here 3 and here 3, total is 6. So sigma 1s2, sigma star 1s2 and sigma 2s2. So now this is what you will get, bond order is equal to half into number of electrons in the bonding 4 minus 2. 4 minus 2 by 2, that is equal to 1, right? So here also the bond order is 1. So that means between lithium we will have one bond. This is clear? Okay, so now you will see the next one, that is carbon 2 molecule, C2. So C2 is having 6 electrons. Now if you remember the order, okay, so you have here 1s of carbon, 1s of carbon. So now this one will give you one orbital like this, okay. Then you have 2s of carbon and 2s of carbon, and this one will give you like this, okay. Then you have 2p, that is 3 bond, and we have 2p, that is 3 bond, okay. Now this one will give you, if you remember in carbon what was the order, that is very, very important. See here, for carbon the order is first pi then sigma, right. So we will have here pi then sigma, and then we have pi star and then sigma, right. So this is your sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then you have pi 2px, pi 2py, sigma 2pz, pi star 2px and pi star 2py, and sigma star 2pz, okay. So now if you have 12 electrons of carbon, right, so 1 2 3 4 5 6 7 8 9 10 11 and 12, okay. So now if we see the order here, carbon, if I want to calculate, this is the electronic configuration and I want to calculate the bond order. So bond order will be half of number of electrons in the bonding molecular orbital. So 1 2 3 4 5 6 7 8, 8 minus 4, right, 8 minus 4 by 4, so that is equal to 2, right. So within carbon there will be 2 bonds. I think I have calculated it correctly. We have 1 2 3 4 5 6 7 8 and 1 2 3 4, okay. Yes, next coming to oxygen. So in oxygen, if you remember, we have electronic configuration, 16 electrons are there. So I will just change this one. See, 1 2 3 4 5 6 7 8 9 10. So in oxygen, what was the order? First sigma 2pz will come, then pi 2p will come, right, in oxygen. So if you remember, we have first sigma 2pz and then we have pi 2px and pi 2py, okay. So now if we have 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 16, right. So if you see the electronic configuration, this is there, then the bond order will be half into, okay, half into number of electrons in the bonding molecular orbital. So that is 1 2 3 4 5 6 7 8 9 10 minus anti-bonding, we have 1 2 3 4 5 and 6. So that is again 2, right. So now if bond order is 2, okay, then you can see here we have 2 unpaired electrons. So this is paramagnetic and this one is your diamagnetic, okay, clear. So now we will go towards hydrogen bonding. Hydrogen bonding, very simple. Hydrogen bonding can be defined as the attractive force which binds hydrogen atom of one molecule with the electronegative atom of another molecule, okay. Now how is this possible? Now see, suppose I have HF, okay, I have HF and here I have HF. Now this is electronegative bond, so fluorine will be more electronegative, so these electrons will move towards fluorine. So that is why I can say that here there is a delta negative charge. Then automatically here will be a delta positive charge. Similarly here it is delta negative, here delta positive, here delta negative, here delta positive. Now because of this charge difference, a small attractive force is generated here which is called as hydrogen bonding, okay. Now hydrogen bonding is maximum in the solid state and minimum in the gaseous state, okay. This one is done. Now hydrogen bonding are of two types, intramolecular and intermolecular. Intramolecular, sorry, I have a small error here. This is intermolecular, okay, means between two molecules if there is hydrogen bonding, and this one is intramolecular, okay, means within the same molecule if it is present. Now you can say within the same molecule there is hydrogen bonding, and here it is within two different molecules, so that is also hydrogen bonding, intermolecular, intramolecular, okay. So yes, now let us do some questions here. This was a homework question from the last class. Corresponding sp2 hybridization is 120 degree. Next, which of the following statement is incorrect? Okay, here I will be telling you a trick to calculate the bond order. Now see, if the, let me write the trick here. So if you have 14, the total number of electrons is 14, bond order will be 3. Then if you just go ahead, okay, it will be 2.5, 2, 1.5 and 1. Now if you go below 13, 12, 11 and 10, it is 2.5, 2, 1.5 and 1. Clear? Now if we see here that the question is asking for O2, O2 2 plus and O2 2 minus, O2, O2 2 plus and O2 2 minus, okay. So 16, 8 plus 8 is 16, so for 16 it is 2. For 14 it will be 3, right, O2 2 plus 3, and for O2 2 minus, that is 8 plus 8 16 plus 1 18, so it is 1. So what is the order of bond order? Bond order will be maximum for O2 2 plus, okay, then we have O2, okay, and then we have O2 2 minus, okay. This is the order of bond order. And now if you remember, bond order, okay, is inversely proportional to bond length, right. So now bond length, what will be the order? The opposite of this one. So we have O2 minus, O2 and then O2 2 plus. Now the first thing is a bond length of O2 is greater than the bond length of O2 2 plus, right. Bond length of O2, is it correct? You have to find the incorrect. Bond length of O2 is greater than O2 2 plus. Yes, this is correct. Bond order of O2 plus, bond order of O2 plus is less than the bond order of O2 2 minus. No, this is wrong, right. So correct answer is option number B. Next, question number 2, which of the following is an incorrect statement regarding hydrogen bond? Is stronger? Yes, this is correct. Small sigma bonds are stronger. This is also correct. Ionic bond? Yes. Now sigma electrons are referred to as mobile electrons. No. Pi electrons are mobile. So correct answer is option number D here. Next, the correct order of boiling point in the following compounds is. So because of hydrogen bonding, H2O has the highest boiling point. So option number B. Okay. Next, arrange the following in the increasing order of their bond order. So now you can see in this species, I will tell you a trick. If the charge is positive, okay, bond order will be maximum. Charge is negative, bond order will be negative. In the same types of species you can compare generally, okay. Or else you can check it also. We know 14, 15, 16, 17, 18, 13, 12, 11 and 10. 1, 1.5, 2, 2.5, 3, 2.5, then 2, 1.5 and 1. Now we have O2. O2 is how much? 16, right? So its bond order is 2. O2 plus, that is 15, it is 2.5. Then we have O2 minus, that is 1.5, and then we have O2 2 minus, okay. So that is 18, that is 1. So now if I want to calculate the bond order, it is O2 plus 2.5, then we have O2, then we have O2 minus, and then we have O2 2 minus, okay. So option number B will be the correct answer here. Next, using, so this is a homework question, using MO2 compare the O2 plus and O2 minus species and choose the correct option, okay. So you can try this question and comment down the answer. So yes students, this was all about the last part of chemical bonding, that is your chemical bonding about molecular orbital theory. This is an important concept. You need to do more such practice questions, okay. So thank you for watching and subscribe the channel and stay tuned for the next class.